presenter is DK Panda from the Ohio State University, who's now teaching in class again. That's always good news. Welcome, DK. Thank you for coming and presenting.
So good afternoon again. It is a pleasure again to this year to meet all of you and share some of the latest things, what we are doing in a virtual mode. Hopefully next year, I'll be able to see all of you in person. So the broad focus of today's talk will be how do we design high performance and middleware for HPC and AI? What are the kind of challenges and opportunities? Paul gave a very high level perspective of what they are doing. As you saw, like continuously technologies are changing, computing platforms, networking, and of course, this new DPU technology. So I'll try to take a look at some of these technologies and see how do we bring all those things, the best features, and then try to design the upper level middleware. So with a high level perspective, if you see, I mean, we are in a very exciting phase. I mean, so we are going through the ExaFlop domain. I mean, 4 years back, we crossed 100 petaflops. Now we have 442 petaflops. Next month, we'll see if this number changes at the supercomputing. But again, the goal is to have ExaFlop systems, and mostly we'll be seeing one might be in the next year. So in this context, I mean, we have the traditional HPC, but as everybody knows, I mean, we are entering into this, the deep learning, machine learning field, and at the same time, the data science field also. So there is a very nice synergy here between these three domains. Everybody is looking for more performance, and once the performance is available, data scientists feel comfortable, they are looking for even more performance. So we are in a very positive cycle here. So then the question is, how do we design the middleware for this kind of environment in a convergent manner so that we don't need a lot of different tools, a lot of different software. And not only we need to run these on-premise systems, we also need to run it on the cloud. So in this context, for last several years, we have been working, can MPI-driven middleware be designed and used for all the three domains? So that will be the central key of my talk today. Of course, MPI has been there for HPC, but as you look for scalability for deep learning, machine learning, data science, do we need separate softwares or can we build on top of MPI? Okay? And I'll try to show you that you can actually try to do it with MPI because MPI has been able to demonstrate that it scales over many different platforms, many different technologies. So you can build all the other things on top of those, the top of the MPI library, and try to get the best performance and scalability. So in this context, I'll divide my talk into these different parts. I'll start with the MVAPICH project. That is the basic MPI project we have been doing for 20 years. I'll soon introduce that if you are not familiar. But I'll spend some time on how do you actually even accelerate applications with the DPU technology, purely from the MPI side. And then I'll try to show how you can build deep learning, machine learning stacks on top of MPI. Then I'll move into the data science application, things like Dask. And I'll also give some examples. As we have been developing the software stacks, we are actually also trying to deploy them in public cloud. I'll show you some samples from AWS, Azure, and Oracle. And for the last few years, we have also started like a commercial spin-up kind of things because of the need in the community. I'll talk about that. That is from Xscale Solutions. Xscale Solution is also a sponsor of this event. And we are also trying to carry out some value-added features in the products so that to address the needs for the community. And then I'll conclude. So I'm assuming many of you must be familiar with the MVAPICH2 project. And if not, we started this project almost day one of InfiniBand. Prior to that, we were working on proprietary interconnects like Mirinet, Quadrix. But when InfiniBand came in October 2000, we were the very first one in the world in my group to jump in and trying to explore how MPI can be designed with InfiniBand, the RDMA features. That was the very first thing we started with. And it was demonstrated at Supercomputing 02, almost like 19 years back. And over the years, of course, we have expanded this to all different interconnects, Omnipath, iWork, Rocky, AWS EFA. We are also working with a newer network called Rockport Networks. We have extended into all different platforms, accelerators, And also we have been evolving with the MPI standard. So the latest we support is the MPI 3.1. As you know, MPI 4 was introduced a few months back. So we are actually working on, and very soon you will see the MPI 4 support also. So currently it is used by more than 3,000 organizations in 89 countries. These are registered organizations. Just from our website, we actually crossed just a few weeks back 1.5 million downloads just from our website. Of course, it is available in a lot of other distros, Red Hat, SUSE, OpenHPC, SPAC, even a lot of vendor software stacks. And it is also empowering a lot of top 500 clusters. Over the years, we have been in this community to try to really push the envelope. So this is the broad architecture. We call it like MVAPICH2 software family. We started with, again, pure HPC. But nowadays, I'll show you, on top of this, we can actually build deep learning, machine learning, and data science stack. So as I said, like we support all the different networking technologies, all the different platforms. But this is where all our research lies. Because we are from academia, first what we do is we really carry out a lot of designs and publish these, take the best set of results or the designs, and then put it into the our MVAPICH2 stack, and we go through very rigorous testing and then trying to release those things. And so that leads to actually a production quality stack. I think in some of the talks I mentioned earlier, we have almost like 200 nodes in my lab continuously doing QA testing. So we can actually try to make sure that we catch all the errors and then make it really a lot of performance regressions we do to get the best performance and scalability. So we have a software family. I'll focus on like three of these main ones. The basic MVAPICH2, that is the base version. Then we have an advanced version called MVAPICH2X, which is for TGAS. We have some INAM integration. And then there is a GDR, which is more for the GPU-based systems for the deep learning, machine learning, Dask, those kind of things. So let me just show you some sample numbers if you want to get a feeling. This is like the very latest release, MVAPICH2 236. That is the public release we did, I think, 2 months back. So here, if you see, this is the very latest platform, AMD Milan with SDR 200. Here it is showing like an Intra-Node within the CPU. Here we can see 190 nanoseconds. We can actually do MPI level communication from a core to core. Similarly, here Inter-Node, we are around like a 1.9 microsecond on this platform. And then see the bandwidth, we are able to come to the peak of the SDR 200, and also within the node, we are able to go to almost like a 42 gigabytes per second. So it's just like a representative set of numbers. Similarly, we support ARM, A64FX, which is actually being used in the Fugaku. But as some of you know, it also has an InfiniBand version. This is running the Ookami system at Stony Brook University here. So here you can see like we are comparing the MVAPICH2X version with OpenMPI. And like here, inter-node latency is very similar. But intra-node, we have a lot of advanced optimizations. As you can see, with more larger message sizes, we are able to give you even better latency. Now, these are just point to point, but as many of you know who are working in the community, the performance of collectives, that is very important. These are the collectives like all reduce, ecast, all to all, because as you try to scale your applications, the bottleneck comes there. Okay? So this is where we have been working very closely with Mellanox and now, of course, NVIDIA with their SARC technology. So these are some results on the TACC Frontera system. This is on the Texas Advanced Computing Center. So this is a full-scale experiment we did, and we presented this last year at the Exascale MPI workshop. So here, if you see, this is like this is running on 7,861 nodes. That is a full-scale Frontera. At that time, now they have added a little bit more number of nodes. So if you see this MPI all reduce, so what we have done is basically there is a SARP, but we have done some additional integration with our MVAPICH2X and with some optimizations. You can see if you compare to the pure software level design, now the SARP, we can reduce it significantly. So here is like a small messages up to 2K. You can see like this is a 1 ppm. That is only one process from every node participating. As you can see, up to 5x improvement we can provide. Short message all reduced. Same thing here happens, reduce. We can give like a 6 kind of improvement. And if you see here, MPI barrier, this is going the full scale. Now you can see on a 7,800 nodes, we can actually have the barrier. Here it's around like it is coming around 40, 42 microseconds. We can do the barrier on completely on this large scale system. So these are like a very important thing. So that means if we can accelerate the lower level communication stacks, especially the collectives, you will see the applications will get a lot of benefits there. So here I'm trying to show some numbers. These have been taken with EPFL. We have been working there. This is their neuroscience application. So they have two modes, like neighbor selection, random or consecutive. We are comparing our MVAPICH2-X with HPE MPI. And here you can see we can deliver like almost 36% improvement if the neighbors are random, or if it is a consecutive, we are giving around 6.5% compared to HPE MPI. So these are some sample numbers, but now let me spend a little bit of time on this DPU technology. I think you have been hearing a lot about this DPU, which Mellanox NVIDIA has started. Now, the DPU basically is a network with some intelligence. Okay, so I call it like a executives and secretary. Okay, so if I show like this kind of architecture, you can see this is the Bluefield-DPU, Bluefield-2 DPU. We have a set of hosts. So you can think of executives. Now, in addition to doing the communication over the standard network with RDMA, now there are a set of RDMA ARM cores. So you can think of like these are secretaries. So just like what we do it in a normal world, like secretaries actually help executives to get tasks done better in any business or any organization. Now, what we have been exploring, can MPI library itself be redesigned to take advantage of such design? Because MPI has a lot of functions, and then if they can actually, some of these things can be offloaded to the ARM cores, we'll try to get a good overlap of computation and communication. So that is the key thing. Just in a normal world, if you see, like let's say executives, you want to set up a big conference call, you need to contact 50 people. Now, of course, the executive can do it, but the executive will spend a lot of time. If it can be offloaded to a secretary or a set of secretaries, while that conference call is time is being decided, the executive is trying to proceed on his or her work. And that will give you overlap of computation and communication, and then the productivity actually increases in a day-to-day world. So same concept, we are trying to take it here. So what we have done, I'll try to show you some numbers. We have done especially non-blocking collectives. I'll go into more details. That is our first initial target, but we are working on offloading or even point-to-point, other kind of one-sided, all the other operations. And this is where like what we have done, this Excel solutions, now we have actually releases. The software releases, we call it a MVAPICH2 DPU library. So this is the August release. We are working on a new October release. So here we have like this is based on the MVAPICH2, the public release version, like the 236. So all the features, whatever is there in the 236, you get there, but on top of that, you get the support for the DPU. So we have implemented at least 3 collectives so far, the non-blocking collectives, all-to-all, all-gather, and IBcast. And this is available. Anybody would like to try it on their systems, please feel free to send a note here, and you will be able to get a trial license. We have actually deployed on several clusters, and we are working with those users. So now let's take a look at some of the capabilities of this. So I'll start with I all-to-all. All-to-all is a blocking, and I all-to-all is non-blocking. So like prior to MPI 3 standard, all collectives were blocking. So that means if I have some computation and I want to exchange some data, let's say all-to-all, I do the computation, and then I do the all-to-all. And while the all-to-all is taking place, the CPUs are just sitting there. Okay? I mean, helping with the communication, but they are not doing any computation. So then what happens as the system size scales, the number of processes scale, the all-to-all takes a lot of time, so you don't get very good scalability. So this is why in the MPI standard, I all-to-all or non-blocking all-to-all was introduced. So that means I can do the computation and I can initiate the all-to-all, but I don't have to sit idle. I can actually try to do additional computation while the things are taking place. Okay? So it is very simple, like as if, let's say I want to go to a movie over the weekend and I asked my friend to come, and it is not that I'm continuously sitting there and waiting for the friend. I can do that, okay? But most of the time what we do is while the friend is coming, I can do my work. And if the friend comes, then we just meet and go. Okay? So that means I am overlapping my task with the activities of my friend. The same idea here. But then the question is, you need two things. One is the underlying network or system should provide the support for the non-blocking. And then the application level, you may need to do some redesign or co-design. Unless you do both these things, you will not get the benefit. So now let's see the first part. So the first part, if you see here, like especially all-to-all, so the question is, all-to-all has been there. A lot of MPI, even the pure host level, people have designed those. But then the question, all-to-all, if you go inside, there are some direct algorithms, there are some indirect algorithms, scatter destination. So for example, I send a message to you. You might have got a message from somebody else. You might need to combine it and send to somebody else. So who does that work? Okay? And in the pure host-based implementation, it has been the host. Okay? So that's why you see when you consider overlap, so here I'm using the standard benchmark, which is available with the OSU micro benchmarks, or we called OMB, is a part of the MVAPICH2 project for last 20 years. We are using the standard benchmarks there. So if you take a look at this overlap, this is the MVAPICH2, this is the red, and then the green is the MVAPICH2 DPU. So as you can see, for short messages, most of the time in the MPI, we have an eager and rendezvous. Eagers are used for short messages. Rendezvous is used for large messages. In the eager, basically CPU does the copy. So you don't see any overlap. And in the large messages, we do this rendezvous. That means CPU has to be involved to make some progress. So that's why the overlap is very low. You will see almost non-existent. But now the question is, can those kind of synchronization operation, rendezvous operations, can be offloaded to the DP? Okay, because we have some ARM core sitting there next to the network, so they can actually take care of that. If I do that, now you see the overlap increases like 98%. Here, if you see, even this is a 32 node, 32 ppm, like 1,000 process runs, you go up to 100%. So that means we are now able to achieve that kind of overlap, what I indicated earlier, what we see in the executive secretary model. So now if you run this OSU I all-to-all, so we have this benchmark where you can actually now put computation while the communication is taking place. So we have the standard benchmarks, anybody can evaluate that. Now if you do this total execution time, that means I had some computation, then I'm trying to do this I all-to-all, but while the I all-to-all is taking place, I also do some computation. Okay. Now if there is no overlap, then they will get sequentialized. Okay, the communication plus computation. But if I can do the offload, so then they get overlapped. And that's what we see here. Now, if you see, like this is a 512 process run, this is a 1,000 process run. So it's the total execution time, this MVAPICH2 DPU will give you benefit. Here you see 22%, 21%, 17%, depending on your system size, number of ppms. Okay. So this is where the true benefit of the DPUs come in. So at least at the collectives level. Now, the question is how we can redesign the application. So this is where we work. This is an example of P3D FFT. FFT is a very common application, but many times the traditional FFTs, a lot of algorithms I use blocking collectives. So we worked with the designer of the P3D FFT from San Diego Supercomputing Center to not only convert these into I all-to-all or non-blocking collectives, but also try to do this reorganization so that while I all-to-all is taking place, some computations can be done there. Okay? So that is the key thing. So the application needs to be a little bit modified. Okay? Otherwise, you will not see the benefit. And once we did that, so this is the P3D application run on 1,000 process. Now you see at the kernel level, and you can think of a P3D FFT like a kernel, we are able to get like all to 21%, 18%, 14% benefits. So these are on a real system. We have run it. We have given live demos. If you have real systems and this kind of applications, you will also be able to carry out this. We are working with some of the people even from UK, Filippo Spica. Some of you might be knowing him. We are working actually on some application. You will see some very interesting results in the near future. So that is like a I all-to-all. Similar kind of things, we have started expanding on other collectives. Okay, so this is a I all gather. Yes, that is also a all gather. This is on a 16 nodes. You can see again, when you combine the computation and communication, we even get a lot of benefits, 48% benefits for large messages, 41%, 39% benefits. So that means the underlying runtime has the potential to overlap the computation and communication. Now, if there is an application, so this is where we are seeing limitation, and really we want to work with the community. If you have any applications where you have these non-blocking collectives, we'll be very happy to work with you. Okay? To see whether you can reorganize your application. We don't have that expertise, but we can actually work with you to exploit this overlap of computation and communication and demonstrate the benefit. So this is another example of IBcast, non-blocking broadcast. It's the same story, 59%, 58% benefit. And very recently, we have done this. It is not released. This will be released in the next release, this October release of the Chapter. Okay? So here you can see we're able to even go for up to 64% overlap. Okay? So these are all the collectives level. And as I said, like we should be able to work with you, people, the application people. Always the applications, the HPCs, always a little bit lag. It's not necessarily a bad thing. As the technology move ahead, gradually application people catch up. So this is where we can actually work with the community to make sure that as the DPU technology is evolving, we can give you a very good solution to really get the benefits here. So I think there was a question in the QA. I can go here. I can see Cliff Addison asked, am I right in thinking the benefits of overlapping communications and computations with DPU look even better when you look at the energy consumed on different processors? The answer is yes. We have not done that kind of evaluation because DPU has the ARM cores. They don't consume a lot of power. But it will still consume a little bit more power than an adapter without any ARM cores. So you'll spend some additional power, but the overall execution time we are reducing. So this is where you see the benefit. So for the given task done, we are able to spend it quickly. So not only it has benefits in the energy consumption, it also has benefits in the total cost of ownership, TCO. It is valid for on-premise system. It is also valid for clouds. For example, if we can deploy this on a cloud, or earlier your application was running on, you were paying for 10 hours. Now you can actually pay for 8 hours. So it will be much more cheaper. So this will be the new kind of the ecosystem will be evolving over the next few years, and then we'll see the benefits. So now let me change the gear a little bit, go into the standard GPUs. GPUs has been there, of course, with GPU and DPU, there are a lot of new opportunities. We have not gone there yet, but I'll try to show you some basic GPU things. I'm sure all of you would have heard of this term, CUDA-Aware MPI. In fact, from my group at ISC 11, we introduced this concept. Now it is available with a lot of other MPI libraries, including MVAPICH2. So the broad idea is that if the GPU and the network, like the InfiniBand, are sitting next to each other, or even NVLink, instead of sending like a data from, if I want to send data from a GPU of one node to a GPU of the other node, traditionally it has been like a CUDA mem copy, then do an MPI send, MPI receive. It takes a lot of time. So can we do it over the network directly? So this is the concept. And if we see here, like some sample numbers, they are very impressive. See, look at the number 1.85 microsecond. This is from node to node, not within the node. We're able to send data from a GPU of one node to the GPU of other node in just like a 1.85 microsecond. So we get a lot of benefits, like a factor of 10x, inter-node bandwidth, we push the benefit, even the by bandwidth also we improve quite a lot. So this is very widely used. Recently, even in our MVAPICH2 GDR, we have taken that to the AMD GPUs also. Okay? So now we actually support both NVIDIA GPUs, AMD GPUs using the MVAPICH2 GDR concept. So this is the ROCm-aware MVAPICH2 GDR. So here we are showing some performance numbers with the MVAPICH2 GDR. That is the latest release. And then the OpenMPI latest 4.1.1 with EFCX support. So now you can see intra-node, we are very similar. Inter-node, we are able to give good benefits for large messages. And collectives, we are able to give you significant benefits. So these are run on the Livermore Corona cluster. And then as you can see, like we are able to give very good performance. So the next thing what we have been trying to do for the last few years, and in fact, we have much more results coming up in the pipeline on the fly compression. Okay? So if you think of the GPUs, Of course, the GPU has a lot of computing power, but the thing always, taking data in and out has been always expensive. Okay? So when you are trying to do some application runs, you take the data, but now let's say I want to exchange the data like all-to-all or even a point-to-point communication. Can I use the GPU cores to do on-the-fly compression? So that means instead of sending like a 2 megabyte message, can I compress and send it for a shorter messages? So in that way, I can improve on my latency, I'll get higher bandwidth, and then the application will benefit. So that's what we have done here. And this was actually, we presented this at IPDPS. It was a best paper finalist. And this is actually available in the latest release. If you want to try in the MVAPICH2 GDR236, it is already available. And here we are showing some results of AWP ODC. This is a seismic earthquake simulation application from San Diego Supercomputing Center and USC. So we worked with them, and now you can see that there are different compression schemes. And in fact, in our release, you can actually select, and there are a lot of runtime parameters to adjust these. Now, compared to the baseline, now you see this is like a GPU computing flops. The higher is better. We are able to push 18%, same hardware, okay? Same GPU, same CPU, with a better middleware with our MPI library, we are able to push the performance benefit by 18%, and then we are reducing the total execution time by 26%, 15%. So this is just the first step. What we have done, this is for point-to-point communication, but we have actually things being worked now for other collectives, even for other MPI operations, and even we are trying to link it with the deep learning. So those are in the pipeline, so I'll not be able to show these results. So they have been submitted to some conferences, but gradually we'll be able to put all those things into our MVAPICH2 GDR library and make it available so that the community can take advantage of it. So here there is another set of results on the DGX2 A100. So this the DGX2 system is getting very popular. So here not only it has a lot of GPUs, it also have a lot of rails, InfiniBand, up to 10 rails. So here we have been continuously optimizing collectives. So here we are trying to show MVAPICH2 GDR with Nickel, that is the NVIDIA Collective Communication Library. So as you can see, so this is up to 32 GPUs. We are able to, for all these collectives, all gather, BCAS, reduce, all reduce, we are able to significantly perform better compared to in the latest Nickel library. This is not yet released. That will come out in the MVAPICH2 GDR 237. But we are giving some early release. If anybody is interested, we can actually give you some earlier version, and you can actually experiment on your DGX platforms. So this is a result from Ookami's people. They are working on a library called HEFFT. And these are run on the Summit system, which used to be the number 1. Now it is number 2. And as you can see, is a performance comparison here across all the different MPI, MVAPICH2 GDR, Spectrum MPI, Open MPI UCX, theoretical peak, and practical peak. We are able to deliver very good performance here. MVAPICH2 GDR is very high, able to give you bandwidth. This is without even compression. With compression, we'll be able to even push it higher. We are actually working with them. They are actually running the experiments, and we'll be happy to bring those results to you in the near future. And here, if you see, as it says, like compared to even Spectrum MPI library and other MPI libraries, MVAPICH delivers you around 10 to 20% faster at the actual HEFFT library. This is another example. We have been working very closely with the Idaho National Lab in the US. So they use the SPETC and then the MOOS. There was a very nice presentation from the Idaho National Lab. We had our annual MVAPICH user group conference. We do every year. It was held in August. So please take a look. So their entire nuclear energy research, their lab is being driven with MVAPICH2. So they see the best performance and scalability with the MVAPICH2 library for that domain of applications. So these are some of the samples what I indicated in the MVAPICH side, but now let me try to move the gear and see how we can take advantage of this MPI library for deep learning or machine learning. So what we have done here, the deep learning, machine learning, some of you must have heard of Horobird or Touch Distributed, Deep Speed. These are the common middleware. And of course, at the top, we have different frameworks, TensorFlow, PyTorch, MXNet. So we have done a very tight integration. Okay? So if you go to this project side, we call it HyDL, High Performance Deep Learning. We have a very nice user guide. You can actually download and build it yourself. And with that, the end users, they just run their application, TensorFlow, PyTorch, MXNet, etc. You don't need anything else. As long as you have our MVAPICH2 library, we provide two paths. One is for CPU-based training with MVAPICH2 or MVAPICH2X, and another is for the GPU-based training with MVAPICH2 DPU. So if you're using any of these libraries, you can build it yourself and give it to your users. You don't need any other library. So within that, let me try to show some sample numbers. I'll show you some MPI-driven deep learning first with data parallelism. But now, of course, as you know, the data sizes are increasing, model sizes are increasing. So we are working very actively on model parallelism and hybrid parallelism. And I'll try to show an example use case. We are working with our pathologist here. It's a real science case in a medical, how do you do a digital pathology? And then I'll try to show some machine learning application. So this is here you can see like a distributed TensorFlow. So this is a CPU-based deep learning. This is like taken from TACC Frontera. Many people say that, yeah, CPU-based deep learning, you cannot really use it, but that is not true. If you have a real large system, you can actually use CPU-based learning. It may not be that good as GPU-based, but it still gives you very good performance. Here on a 2000 node on the TACC, we are able to get like a 260,000 images per second, and it's very linear speed up, you can see. And the entire ResNet 50, we are able to train in 7 minutes on this system. Here, these are some numbers on the GPU-based system. This is on the Ookami Summit. Here, we are able to scale to like a 1536 GPUs with the ImageNet 1K, which has 1.2 million images, and we are able to train in 4.5 minutes. Okay. Now, we have done a lot of comparison here. We are trying to show this. These were done on the Livermore-Larsen system, which is a up to 256 voltage GPUs. And what we are comparing here using our integrated framework, either you go for touch distributed or Horoward or DeepSpeed, compared to the standard nickel-based library, our MVAPICH2 GDR will give you almost 10,000 images per second faster. Okay? Because we have much more highly optimized collectives, and then that pushes the boundary. So those are some basic data parallelism results. And as I said, now if you take a look at like the input image sizes these days are continuously increasing, model sizes are increasing. Now, if you take a look at like how much memory is available in different GPUs, CPUs, at some range, you see data parallelism is impossible to be done. Okay? So this is where you need to come up with model parallelism. Okay? So we actually presented this paper at ISC 20. It is available in archive. We call it hybrid parallelism or HyPar-Flow. So if you use that HyPar-Flow, so here we are showing on TACC Frontera, like 512 nodes, we are able to get 481x speed up. Okay, so this is again a pure CPU-based deep learning with hybrid parallelism. We see very good efficiency here. And these are with the GPU from the Livermore-Larsen system with up to 1,000 GPUs. So we have this framework called GEMS. It has some different components. But the best solution here, if you see the higher is better, like the GEMS hybrid master, that design is able to give you almost 97% efficiency on 1,000 nodes. Okay? So we are able to scale. Now, the next level, what if the challenges are coming, even the model parallelism also has some limitations. So now the question is, can you go into some sub-graph parallelism? Okay? So if you take a look at some of the transformer models, which are being very extensively being used in BERT, speech processing kind of thing. Here it is trying to show, given a set of GPUs, how we can take this bigger graph and effectively balance it out. Okay, so that is what is the subgraph parallelism. So think of it like a mapping. Just like for a given application, you try to do a best mapping. Here we can actually take the DNN models and then try to have a best matching here. So this paper was presented at IPDKS earlier this year. And now if you see, here we are trying to show compared to the data parallelism. So this is like the red line. Our new, the super parallelism, we are able to reduce we get almost factor of 3 speed up in 1,000 GPUs. So we are able to accelerate the DN training by factor of 3. And so this is a very active research in my group we have been doing, and These solutions are already available in the literature, so you can actually try to use these for your applications. Here, I'll try to show a very concrete showcase where it is very important. It's AI-driven digital pathology. So the question is, I think all of us know about the pathology. I mean, we go to doctors, we give samples of bloods, and then pathologists take a lot of time to analyze it. But pathologists are also very expensive. So the question is, can we train the system or a machine to do a lot of analysis, and based on the past data, because every hospital has millions of images, and they can narrow down the probable disease, and then the pathologist can actually come and then verify it. Okay, so that is the kind of things what we are working here with some of our pathologists at the Ohio State University. So these images are very dense, 100,000 by 100,000 pixels, very large. They call it whole slide images. The standard practice has been to divide into tiles, okay, just like the traditional HPC. But if you divide by tiles, you lose a lot of information on those boundaries. So you cannot dictate a lot of those patterns. So we worked with them. So their thing was actually taking even one node with 4 GPUs, they were taking 7 hours. And with one GPU, it was taking 32 hours. So they were not even very brave to go and try to develop advanced models. We worked with them. We presented the results at SC 20. So now you see with one node, 4 GPUs, with 32 nodes, 128 GPUs, we reduced to 0.46 hours. Okay? So we almost gave an 22x improvement. Okay? So what it means that this is becoming very realistic. Okay, so these people are now very happy to go into their next model, so that they can not only, earlier they were targeting only these patterns, so now they can actually handle much more complex patterns, and then we can actually train. So this is a big project we are working at OSU. So those are the deep learning. So let me also try to touch a base a little bit about machine learning. The same idea like the QML, that is a kind of the middleware, which is very widely being used in the machine learning. So what we have done here, the same MPI-driven solution. So this is available. So there is a package MPI4Pi that has been running with Nickel. So what we have done is we have done the linking with MVAPICH2-GDR. So we have a release here. If you want to use it, please feel free to download here. And now if you see, these are like the standard, some of the benchmarks in the machine learning domain, K-means, linear regression, nearest neighbors, truncated SVD. We presented this at ML-HPC workshop last year. And compared to the Nickel solution, now you can see we are able to give benefits almost by a factor of 1.6, 1.4. So your machine learning applications can run much more faster. So then we are taking the same framework, like as I indicated, the same storyline, saying, can the MPI-driven solutions can actually help even the data science application? And especially in the data science, there is a newer framework which is getting a lot of attention called Dask. And so there we have done a similar kind of designs. There is an MPI4Dask. The Dask had some support on the TCP, had some support on the UCX. So what we have introduced is modules MPI4Dask and MPI4Pi, and that is linked actually with MVAPICH2-GDR or even with MVAPICH2X. So then you can actually run it, the Dask, on CPU-based systems or GPU-based systems. So this was our second release we did earlier this year. If you are a Dask user, you can actually download and use it here. And now you can see similar benefits we see here. These are some benchmarks compared to IP over IB, which is like the TCP/IP emulation over InfiniBand. This is the UCX. And now you can see using our MPI4Dask, you almost get benefits of factor of 3.47, 6.92x. This is another benchmark, CUDF. On the GPU-based systems, we get 2.9x, 2.9 benefit. So the idea what I'm trying to drive here is that if you have a very good MPI library, of course, I'm trying to show this with MVAPICH2-GDR or MVAPICH2 library, but it is applicable to other MPI libraries. So any MPI libraries, if you have the additional modules, you can actually plug them in and you will be able to actually satisfy all these users. You don't need any other library or middleware. So now you can start combining some of these things. I talked about the GPU compression earlier. So the question is there I showed for the HPC application, now can I actually use it even for Dask? Because the Dask uses GPU and I can do also the on-the-fly compression. And this was also a part of that IPDPS paper. So now you see on the Dask, we are able to even push the average throughput by a factor of 1.56x and reduce the execution time by 37%. So a lot of these enhancements, what I've been talking at a GPU level, DPU level, network level, CPU level, these are combined effects. So we can actually combine all these things, and based on your communication pattern, IO pattern, we'll be able to actually give the benefits. So as we have been providing these kind of solutions, people are able to download these. We are also working with the cloud folks. Already with the Azure cloud, MVAPICH2 is already included. It's a part of their CentOS HPC mesh. So you can migrate your on-premise applications to cloud very easily, the same environment. Here I'm trying to show some numbers with their latest NDV4 instance. So it has actually eight rails of HDR200 and A100s. So here again, basically that GDR kind of performance, what I showed earlier, we are able to deliver in a much more bigger manner. Like here, if you see the bandwidth, this is the GPU to GPU intra-node, 133 gigabytes per second. We are able to do the transfer here. And then outside, of course, it is the same SDR level performance we have. Similarly, we are working with AWS. As AWS, as you know, they don't use InfiniBand. The Microsoft Azure, they use native InfiniBand. So a lot of our stacks will run there with some additional optimization. But AWS uses EFA, that is the Elastic Fabric Adapter. They utilize a lot of RDMA concept, but it is not IB. Okay, so we have worked with them, and we have a native design, okay, of MVAPICH2 and MVAPICH2 library, the software family with EFA. They also provide support through OFI, so other MPI libraries run on top of that, but we have gone to the native design. So here you can see this is their latest ARM HPC instance, comparing with MVAPICH2X with OpenMPI for already used scatter. Here are some representative numbers. We are able to show benefits. These are actually WRF runs. These are very nice application. Many people use it on the cloud. As you can see, as the number of processors are increasing, this is comparing with Intel MPI and OpenMPI, we are able to scale. And especially as the process sizes increases, because this is a native design which is done with the EFA, we are able to scale far better on the AWS. And recently, we have also started last year engagement with Oracle with some funding. So we have actually another deployment is coming out. They are deployed in their HPC system. So this is the Oracle Cloud Infrastructure. So here you can see again some collective performance. I'm trying to show Bcast and reduce compared to MVAPICH2X. The Intel MPI and HPC-X. We are able to give, in fact, 2.7x better, 21x better performance. So those are the kind of the cloud numbers. Let me wind down. These are all available from the OSU side. These are pure research. But over the years, we have received a lot of requests from really providing commercial support. Because from OSU side, we provide support, but those are best effort because we are a research organization. But people want really a commercial support. And that's what we have done. We started this commercial spin-off 4 years back. And through these, we can actually participate in bidding, participate in RFPs, provide a commercial support for HPC centers. So we are being provided a lot of national laboratories and international supercomputing centers. So if some of you are interested, we'll be very happy to talk from that side. But there also, we are trying to provide some value-added products. So we have actually, I talked a little bit about MVAPICH2 DPU, but we also have an Xscale HPC, Xscale AI product. Xscale HPC, as it stands now, it is very much similar to the MVAPICH2, but a lot of additional optimization has been done for platform-specific things. Okay, so that because you know MPI, if some of you are familiar, within MPI, any MPI library, there are almost 200, 300 parameters, runtime parameters. So and the cluster architectures are changing very rapidly. So you need to give a lot of these parameters to get the best performance. So that's what is available in the Xscale HPC. Then in the Xscale AI, what we have done is I indicated about the integrated environments. We have actually done all those integrations. So as an end user, you don't have to even spend 5 days or 7 days to do that. You can just download and a one-click deployment. You should be able to be ready with your providing to your user TensorFlow, PyTorch, or any of those things. But one more important thing we have added there is called deep introspect. So the idea here that this is shown through these, when you are running a deep learning applications, many times, because you are using a lot of these stacks, might be a Nickel library below, or an MPI library below, then Harvard, then TensorFlow. There could be a lot of mismatches, okay? So that means you may not be knowing you will get some results, but the question is, are you able to utilize your system 100%? Okay? So this is where we have developed these value-added things called a deep introspection capability. So this is like a dashboard. While the job is running live, you can actually see what is happening to your all reduced, in this example, like all reduced message distribution, latency. So very quickly you can find out, for example, here, see like many all reduces are being called in this message range. So the question is, are those optimized or not? And here, if you see, like all of a sudden, this range, it's not optimized. The number should have gone like this. So that means you need to take that optimization. So very quickly you see in your system, where are the bottlenecks? And as soon as you tune them, you get actually the higher and higher benefits. Okay, so that means you are able to give you better returns for your users or your cloud providers. So this is what we are trying to provide there. And then I, of course, discussed the Bluefield-DPUs earlier from the HPC side. We are also working on the deep learning side. How do you take advantage of the DPUs for DL training? Okay, so we also use that executive secretary approach. We presented a paper here at Hot Interconnects 2 months back. You can take a look. Here are some of the numbers. You can see like this, the ResNet 20 DNN training with the Bluefield-DPU, even just with 16 nodes, okay? We are able to give you 14% improvement. Just on 16 nodes. The DL training can run much more faster. So this is a release which will be coming out again in the MVAPICH2-DPU from the Excel side. So with this, let me conclude. So what I motivated, like the upcoming ExaScale system and cloud need to be designed with a holistic manner, taking a look at not only HPC, deep learning, machine learning, and data science. I provided some of the opportunities that are coming because of the advances in technologies, and I presented some of the solutions. And of course, we are in a very exciting phase. I think Paul also indicated there's so many newer technologies are coming. How do we really build the software stacks or the middleware stacks? And here I indicated through MPI-driven solutions, you can actually try to handle all these things. So with this, let me thank all our sponsors. These are all the sponsors who have been working through funding and equipment donations for many years. But last but not the least, these are all my heroes. As you can see, this project, what I'm trying to bring it here is a work of 20 years. We have been building, so these are all my heroes. And while we have a lot of people, we are continuously looking for also more and more qualified people. So I just want to show this. We have a lot of positions available at the OSU side, also on the Excel side. If any one of you would like to come here, please feel free to send me a note. With this, I'll stop here. If there are any additional questions from the QA or chat box, I'll be very happy to answer this question. Thank you.
Thank you, DK. I see you've already addressed Cliff's question. So I'll just open it up to the panel to see if there's any additional questions. Glenn or Mark, anything?
So yes, DK, thanks for a great talk. You talk quite a bit about the use of using DPUs and taking advantage of them. Is that a direction you think a lot of systems will be going in the future, as in having a significant DPU component added to them? As in, we be thinking of it in the design of them. Is this something we should be taking account of, essentially, what you're doing with the MVAPICH?
Sure. If you have, so I think I'm just giving a very generic answer here. I mean, anytime we see the new technology, even I can go back 20 years, even Gilad or Mellanox people can certify. When InfiniBand came, a lot of people were also skeptic, saying that, okay, will it work? Will it deliver? Okay. So unless people see some software solutions which are really running and then see the benefits for some applications, then people see the benefit. Okay. So we have been like that kind of an enabler in the community for the last 20 years. So I'm just trying to show the DPU some initial results, but of course we have to demonstrate these. I mean, so I'm saying from our side, from a research side and development side, to show the capabilities. If we can show it for 5 killer applications, I'm sure it will pick up. Okay? But there is always that kind of a period where it's a wait and see game. like the real end people are trying to wait, see that will it give me benefits? Of course, there is a cost performance benefit. I'm not reaching there. That is left to Gilad and the vendor providers. But for people like you, if you have an HPC center, if you have applications, we'll be happy to work with you. And the answer may be yes or no. It'll come out of the research.
Okay, great. So we should talk more about that offline. About
sure. If you have a DPU cluster, we'll be happy to give you like MVAPICH2-DPU install there. Let your users work on it. We'll work closely with you and then see. As I said, the applications may need to be modified. At least the examples I gave. Okay. Yeah. But we are working on some solution. Again, it's not public available. It may not need those changes. You will see in the next 5 to 6 months, we will have some of these solutions coming. Mm-hmm. Okay? So in that way, the applications will in fact see much more benefit.
Yeah, that becomes really interesting then because it's easier for everybody. Yeah,
that's correct.
Yeah, great. Thank you.
Thank you.
Thank you, Mark, for the question. Gilad, sounds like you have a question too.
Yeah, no, I have a comment, I have a question. It's always great to see DK presenting a progress of development capabilities and so forth that coming into the communication frameworks. It would definitely be an interesting presentation actually to show the progress in the last 20 years. Many years ago, the focus was to try and cut latencies. If you remember, network latencies were in the 10 microsecond range, yes, more or less, right? It's like you can go around the world twice before the data goes from one side to another side. And then the focus was to reducing those latency in a sense. And after reducing those latencies and getting to much smaller latencies for moving data compared to the latency of the MPI algorithms themselves, this is where it started to to change and having a focus of having computing, for example, in more places where you can move algorithm to run them in more ideal place. And that's an example of doing reduction on the network, right? Because you can have network latency at 0, but if you continue doing reductions on an endpoint, you will not solve anything. So that was kind of another move, right? Started to actually move algorithm outside of endpoint or traditional endpoint and start putting them in other places. Now it looks like we're kind of going to another phase where we're saying, okay, there was a good fight of reducing latencies, but in order to kill latencies completely, maybe the best approach is actually to go overlapping, because once you do overlapping, there is 0 latency. And that's kind of the biggest or more important thing right now. And the same that we talked about neural networks in the 70s, but could do nothing with it, and actually needed to wait decades in order to have enough data and enough computing resources to actually do something useful with it. The era of AI. Non-blocking operations, for example, were part of MPI3 specification many years ago, but there was no real usage of it.
That's correct.
Now the kind of the infrastructure, right? The architecture of the infrastructure enables you to start leveraging the non-blocking operations. And it's a great actually to see the releases of MVAPICH2-DPU, for example, that can start doing that, right? It's kind of moving MPI to actually outside of the CPU, the whole CPU, and start running MPI in different places to hide latencies completely. I think one of the challenges that we need to join forces is start to get applications to adopt those changes, because so far the application didn't need to change and DK improve MPI, and that's kind of application seamlessly were able to gain the performance advantage. But now actually we're looking on areas where we need to start looking on applications that were written 20 years ago in a wrong way. It was a good way 20 years ago, but now it's actually not an effective way. And drive that work as well. Yes. And this is where programs like Scalable, for example, or programs between applications and research centers and universities and the teams like DK and so forth can actually go and do or take the code design into the next level and start looking how to modify the application to leverage non-blocking operations. Great example, your team DK working on FFT and taking the three-dimensional and says,
Yes.
if we change it, it's a great boost, right? It's like we can hide latencies. This is one example. So definitely hoping to see more and more and more in anything that we can do from the council perspective or any other hat that we wear. We definitely want to support it and drive that. I think this is kind of one of the big things in the future.
Yeah, we are always available. As I said, we'll be very happy to work with the community like we are doing for 20 years.
Excellent. Thank you, Gilad. Thank you, DK. Appreciate the presentation as always.